So as a bit of a recap now, as a recap of our topic on friction, what we learn is that friction is a force that opposes the motion of a given body. So we see that a body will eventually come to a stop when it is moving because no, it is affected by what we call frictional force. No? Now, frictional force provides us with advantages, with disadvantages, and we see that one of the main advantage of dealing with a force is that our force allows us to walk, no? Allows us to move from one point to another. No? So that's one important feature no, of our friction. Now, disadvantages, I think one of the major thing that we can cite no, from the disadvantage of friction is it causes the wearing down no, or the a particular kind of material or device no, will wear out no, once there's too much friction. No? So that's what we want to avoid no, when we deal with friction. And friction also creates this heat, and sometimes this heat no, is causing no, the inefficiency of equipments. No? So when something heats up or is difficult to move, no, then it also adds to the inefficiency. No? So it creates the result, the end result of friction actually is heat, no? Which is sometimes not good. No? So again, things that is advantageous, disadvantageous. No? Now, for our friction, we can also increase it, no? And we can also decrease it if we need no enough amount of friction, then we need to increase it. No? So we realize that it depends on the kind of surface that we are dealing with. No? It depends on the state of the body, whether the body is not moving or moving. No? So we can increase the friction there. No? Now, when we want to decrease or reduce friction also, then we can also use a specific material that has less friction. So supposing now we use instead silicone plastic now rather than using rubber. No? So that's one way to resolve the problem of too much friction. No? Or when we use also lubricants. No? So for our lubricants, we have oil, we have grease, no? And many other materials that allows us to reduce the friction between the contact of surfaces. No? So friction is there when surfaces come in contact with one another. No? So here are things that we see about its advantages, no? And likewise now the disadvantage. No? So we buy constantly a new shoe or slippers because the old one now was worn out no? Because of its contact with the floor. No? So that's one thing that we notice with the things that comes in contact now that are constantly rubbed no? With one another. No? So they kind of worn out, no? They wear out no? Or they get worn out. Now here are methods of how to increase friction. No? So spikes is one. No? So like when you play a game no? In a field, so some shoes are intended really not to have spikes so that when you make a forceful move, no, you will not slip, no, hindi ka matumba, hindi ka madanlog sa ground, no, like in a football field, no, or in a golf course, no. So the players there now will make some very strong swing, no, that they really have to anchor themselves no, on the ground. No? So they have these shoes that have some spikes. No? Now, ways to decrease friction also, no, or to minimize the development of heat. No, so we use lubricants on things. No, so also no, some devices like a bearing, no, will also allows us to reduce the friction no, between surfaces that are in contact. No? Now, here are factors that we identify. We identified three of them, no? And they have a direct effect, no? On the amount of friction that is present, no? Between surfaces that are in contact. So the first one that we identified is the nature of the surface. So if the surface is made of rubber, if it's rough, no, then it will definitely create this frictional force. No? Now, what we see is that the applied force is always uh, moving in one direction, and the red line here that goes in the other direction is known as our frictional force. No? There are times when the frictional force and the applied force are equal, but there are also times when the frictional force, no, is relatively smaller, no, than the applied force. No? So cases like when things are sliding, no, or moving, maybe in those instances, we may have, no, a lesser amount of friction than the applied force. No? Okay, so that's the first factor that we identify, no, the nature of our surface. Now, the next one is the state of the body, you know, whether the body is completely at rest or the body is in motion. They have no two distinct or different amounts of friction. No? Now, we call the first type as static friction, no? The one that causes the body to not to move. No? Now, when you try to push something, no, that that force that you are using, no, is you really have to exert, no, so much force there when you would want to move something, especially if that object is quite heavy, no? Like a box filled with many things. You really have to push, no, with enough force there to be able to slide it. No? Now, the force that is causing it, no, to start, no, moving is usually equivalent to the friction on the ground. No? We call that as the static or starting friction. No? So before the body slides, there is that force there, no, that you really have to increase, no? Which will be considered as your static friction. You have to overcome that static friction to make that object move. No? So not until you are able to overcome that static friction, that object will remain at rest. No? Now, however, when the body is already in motion, that starting friction, no, will now get lower. No? So static friction is the highest, but as the body starts to move, then that frictional force will now reduce. No? Now we call the force now or friction now that causes it to move. No, is we call it as the kinetic friction. So the first one was static, and this one is the kinetic friction. Now usually kinetic friction is labeled with F sub k. No? There's a small letter k there to denote kinetic. So this is a friction that is occurring, no, when the body is sliding already. No? Now, we call that sliding friction or kinetic friction, and this is usually, you know, smaller. The kinetic friction is smaller or lesser than the static friction. So between the two, no, the amount of friction before the body starts to move is usually, no, the highest. No? Actually, there are three types of friction that we will learn, no? And the last one, which is the least amount of friction, is known as rolling friction. No? Now that rolling friction is observed now between the tire and the road. Now you notice that the tire here now of the car is not actually sliding on the road, but it is revolving. No? So it rolls. No? Now that friction that is present between the tire that rolls on the road and the concrete now is known as rolling friction, and that's the smallest of these three types of friction. No? So highest is static friction, then followed by kinetic friction, but the least of them is the rolling friction present in bearings, in tires. No? Now we don't see a tire of a car that is made, no, in a different shape. No? But basically, no, tires are usually round, no, circular. No? I have not seen that it's made as oblong in shape, no, or square. No? Just imagine yourself, no, riding a car that has an oblong tire. No? So maybe, no, it seems that the road is bumpy. No? That if it is made, no, like that, no, oblong. No? So again, no, rolling friction is the least of all of this. No? But I think in this slide, it's not mentioned. No? So static versus kinetic friction versus rolling friction. Now the third type, now which allows us now to set up our equation, we call it as the normal force. Now with big letter N. Now we can name our normal force as total normal pressure. No? Now this one is present when a body is actually it is in contact with another surface, no? Like a table, no? On top of it there's a box. So we realize that there would now be two forces present, no? One that goes down, which is due to the box, no? Which we call as the weight of the box, and the reaction of the table, which we call as the normal force, no? Now this is an action-reaction pair, no? And these are two forces that are occurring on two separate bodies. No? So the normal force will push the box up while the weight of the box will be pressing down on the table. No? But basically, you'll notice that if that's an action-reaction thing, that weight and the normal force will eventually be equivalent to one another. No? Now, one thing we realized that the normal force in this equation happens to be proportional to the frictional force. No? Now, in that case, when they are proportional, then we can make that into an equation by adding a constant of proportionality. No? Now, our constant of proportionality, which we will call as the coefficient of friction, indicated by something like this letter U with a tail. No? So we call it as mu. No? So this is mu n in this case. So that is now equivalent to the frictional force. No? So mu there is our proportionality constant. And the value of mu is usually between 0 to 1. The value could not exceed more than 1. No? So the value there is commonly equivalent to a decimal number. So like 0.1, 0.2, 0.9. Now, when the value is almost equal to 1, if mu is almost equal to 1, then that signifies that the surfaces are having a very high degree of frictional force. If it's almost equal to 1. If it's almost equal to 0, then the two surfaces that are in contact happens to have the least amount of frictional force. So actually the value of mu is telling us whether there's a high degree of friction or not. Now, usually, the pairs of materials that have the highest value of coefficient of friction or mu, is the pair that is rubber and concrete. So, since they have the highest coefficient of friction, that's why we use them as a pair of materials that is used on the road. We don't replace our tire with a different material. Maybe, I don't know, in the future if they will be able to invent something that will exceed the coefficient of friction of rubber and the concrete road. If there would be such a material that will be actually equal to 1, then maybe we will replace our rubber tires. But until then, I think the rubber tires will stay as is. Because again, that's the type of material that is best suited to provide us with the safest way to stop a car. The rubber. Okay, so again, with the value of n, this one now allows us to create our equation for our frictional force. So our frictional force is labeled as F is equals to mu times n. And I want you to remember that expression. Now, using that equation, we will try to go into our first problem. So let's try our first item. So let's have our first sample problem here. So we have here a loaded box that weighs 600 newtons. It is pulled along a level floor with a constant velocity by means of a rope. And this rope happens to be parallel to the floor. Now, the coefficient of friction, as they've mentioned, is equivalent to 0.12. Our question is, what is the tension in the rope? So usually, the tension is equal to the force, which allows us to pull the given body. Okay, so let's ponder upon this problem. Okay,
Yes,
so
sir.
Yes, sir.
we illustrated a box that is weighing 600 newtons. There's tension that pulls it to the right. So actually, we can draw the rope or tension going left, but let's just assume that it is being pulled to the right. There's a U sub k, mu sub k equals to 0.12. And that is our coefficient of kinetic friction that is present between the box and the floor. So the floor, since it is in contact, since you are rubbing it against the box, then there would be coefficient of friction. Now going to the other side, if you are actually pulling it to the right, then on the other side, so if we draw our free body diagram now, so we will now complete our forces here. So you'll see that there would be an F sub k value or kinetic friction that will move left because the motion is seemingly going to the right. Now, when there is weight, then naturally the floor will now exert a force upward. And usually this value must be equivalent to our weight. Now we call this force here in the other direction as N. So if it's an action-reaction thing then we can actually find how much is the normal force here. So what is our goal? We are trying to find the tension that is found on our string, so or on our cable. Okay, now what equation can we use? So first of all, our equation is that friction, Fk, if we'll call it F sub k, is equals to mu sub k times N. So mu is your coefficient of friction, and then N is your normal force. Now we know the value of the coefficient of friction, but ang question is how much is N? Now, if we'll divide our forces here into two types, so we can actually have vertical forces. So forces that are found along the vertical line. So these are one, your N. Normal force is going up. And along the vertical line, there's also weight that goes down. If in our vertical axis there are two forces present, we can probably call it as F sub y, forces along the vertical plane or y-axis. So one is N that goes up, W that goes down, and we notice that this body now is not actually moving vertically. So this is not moving up and down. It is simply sliding left and right, but it's not moving up and down. So we can say that the total of these two forces present vertically must be equals to 0, because the forces there are considered balanced. Since the forces are balanced, then we can say that N minus W is equals to 0. Then from that equation, we can say that N must be equals to your weight. So if N minus W is equals to 0, then N must be equals to W, and therefore N must be equals to 600 Newton. So your normal force on the vertical axis is equals to 600 Newton. Now let's look at the horizontal axis. Now what forces are present on the horizontal axis? Now one of the given in this problem is that this body is moving with constant, no? It is moving with constant velocity. No? That's one of the implied, no, statements, no? Or one of the statements that we can get. No? So this one is moving with constant, no, velocity. And when we say that there's constant velocity, the acceleration of that constant velocity must be zero. No? We already know that, no, from our uniform motion. Now, if acceleration is zero, then we will also realize that if F net, no, is dependent upon acceleration, and if acceleration is zero, then the net force must also be zero. No? And again, no, this one is only possible when we are dealing with balance forces. No? So if we go into the horizontal forces, no, and the horizontal forces, no, are responsible for the motion, no, along the horizontal axis, but the motion there, no, is having a constant velocity. No? Then we will see that along the x-axis, no, which gives us tension that goes right, frictional force that goes left. No? Dua mo lang na sila, no? One that goes right and one that goes left. Now, if that's causing a constant acceleration or constant velocity, then the net force there now must be equivalent to zero, no? Because there's no acceleration that is occurring, no? So no net force is present. No? Now, if this is also the case, now that P and minus Fk is equal to zero, then we will realize that P here, no, can also be equated to F sub K, no? If they are, no, equal to zero. No? Now, to solve for F sub K, we realize that that's U, no, sub K, no, times N. And we understand that mu sub K is already provided. Now, mu sub K is equals to 0.12, no? While N is 600 Newton. So if you will get the product, now how much is our product? Okay, so the product that we have now for our tension now, if you multiply mu, which is the coefficient of friction, which is 0.12, no, times 600 newtons, which is our value of N, no, from the vertical forces. Then the tension there, no, which is equals to the kinetic friction, no, should be equals to 72. No? So we see here that the body here is moving, no, very, very slowly. No? There's no acceleration actually. No? But this one is sliding to the right. No? But in order for you to have that, no, you must have a balance force. So again, no, the assumption here is that there is no acceleration occurring. No? Balance forces. So again, this is the solution that is provided to us now without the aid of a free body diagram. But I believe, no, a free body diagram is a better approach, no, so that we will know, no, the relationships of the friction to the tension, no, the normal force, no, in its relation to the weight of the body. No. Now let's go to another example, number 2. No. So let's see, no, our number 2. So we are provided here now in number 2. So if the rope there now forms a certain angle, which is now 30 degrees, no, we are still asked to find, no, the tension. No? Okay, now let me cover this one again, no? And let's have some illustration. Okay, so if we draw our situation there, now we are looking for our tension T, which forms an angle 30 degrees now with some horizontal line here. No? Now, if you will notice, now we will still observe here that our tension T there now, since it has now an angle, will now create now something like two types of two types of components of forces. No? One which is horizontal, no? And the other one, no? Which is now vertical. No? Now, usually we label that as our no, horizontal component Tx and the vertical component T sub y. No? What we know no, to get our components of our forces T sub y and T sub x, T sub y is dependent on our sine function. No? And that's dependent on T sine 30 degrees. And our T sub x, no? Which is our horizontal component, is T cosine of 30 degrees. Okay, so these are our components of our force. No? Now, we see that T sub x will cause this box no, to move to the right, while T sub y will seemingly no, cause the box there to move upward. No? Now, our body, if this one is sliding to the right, no, then there's going to be a force that goes left, no, which is called as our frictional force. No? And usually our frictional force Fk is less in value. No? But still, no, it will be there. No? So the action of the T sub x value going right will cause the opposition of the force, no, called F sub k, no, that will move left. No? Now, with the weight and the tension there, now the surface will push the body upward also. And we call now the force that is causing the box no, to be pushed up as our normal force. No? Now, if we try to find now no, or split our forces according to their direction, no? So we can group one set of forces as those that goes vertical. No? And our vertical forces, we can call it as F sub y. Now, two of these forces that goes vertical are pointing up. One is pointing down. What are forces that points up? Normal force, and your T sub y is pointing up. While W is going down, no? But the body there no, is still believed to be no, in a state of balance. No? Because the body is not actually moving. No? It's not moving vertically. No? So these three forces, when you add them up now and consider their direction, their total is simply equals to 0. No? Okay, so we have our F sub y no, value. No? Now, the main thing that we would want to find here is n. So therefore, if you will find the value of n, no, then we will see that n will be equivalent to W no, minus T sub y. No? And if we substitute that, no, our n value is actually equivalent to 600, no? Which is weight, minus T sub y, which is T, no? Sine of 30 degrees. No? If we'll try to find n there no? And get the value of sine 30 degrees, I think the decimal equivalent of sine 30 degrees is it's equals to 0.5. No? So 0.5 T, no? Because sine 30 degrees is 0.5. So you can get your calculator and try to find no, the value of sine 30 degrees. No? So eventually, no, from your vertical forces, you can have this resulting equation. No? So we could have this one. No? So this is our resulting equation for our vertical force. Now, horizontally, how many forces are present horizontally? No? Now, on our horizontal axis, no? So the horizontal forces, no? Our horizontal force, or Fx, no? We have only two. No? One that goes right, which is your T sub x, and one that goes left, no? Which is your F sub k. No? And we still say that this is sliding So probably there might be a net force, no? But since the acceleration again is zero because this is moving or sliding now with constant velocity, that the total there is simply equals to zero. No? Again, not zero because again, no, it's the same case, no, that it is a balanced state. No? So from there, no, if fx is t sub x minus f sub k, that t sub x can be equivalent again to fk. But fk is equals to mu, no? Mu sub k, no, times n, no? Which is relatively not the same expression that we have earlier. No? Okay. So what is our t sub x actually equivalent to? So t sub x from our equation above here, this is actually equals to t cosine of 30 degrees. No? While f sub k, no? So that's your t sub x. F sub k is mu, which is 0.12. No? And n being equals to 600, no? Minus 0.5 t. No? This is the one that we have earlier. No? So this is our value of n. And then therefore, you'll notice that we are left here with simply, no, a variable t. No? Now, I want you to get first, no, the value of cosine of 30 degrees. No? Can you get for me the value of cosine 30? Now, again, now, when we end up with our equation t cosine 30 degrees, which is equals to our t sub x, now, and then our f sub k being mu k times n, no? And again, mu or coefficient of friction is 0.12, no? N is equals to the one that we see on the left side, no? Then we can actually distribute the value of, no? We can distribute this value 0.12, multiply it to the product, to the value inside the parentheses. And we get this one, no? 72 minus 0.060. No? Now, using our knowledge in algebra, we combine together all same letters. No? So 0.87t, and we add to that, no, 0.060. No? And this is equals to 72. Now, the total on the left side now will be 0.993. No? Am I right?
Yes, sir. 93.
Okay, then I think we will be dividing both sides by 0.93 now to be able to calculate. And that will now leave us now with a value t. No? If you divide 72 by 0.93, how much is your tension?
77.42, sir.
Okay, so we have 77.42 Newton. No? Okay. So when we combine together 0.87 with 0.06, no? So we end up with 0.93, no? And then what is left on the right side is only 72. Dividing this by 0.93, now both sides now eliminates the decimal number. No? Now that leaves us now with tension, no? That is 77.42. No? Now earlier our tension was how much? Was it lesser or greater ang atong tension kaina?
Lesser, sir.
So there's less friction or less tension when the angle is horizontal. No? But when you make the angle a little bit, you're forming an angle, no, that is 30 degrees, then maybe now you'll have to use, no, a greater amount of tension for that one. No? So that's maybe, no, something that we can get from this problem. Okay, so again, here's our other solution. No? When we want to find our tension, no? And of course, no, the corresponding illustration. that we will probably make use also of the knowledge. When force is forming an angle, then it will always have p sub x and p sub y, or horizontal and vertical components. No? So we have a very close answer here. No? Okay, so any question from the class? No?